Hello, my name is Serena, and our presentation is on power series. So a power series is a series in the form of the summation from n equals 0 to infinity of c to the n x to the n, and the expansion of this is c to the 0 plus c to the 1 x plus c to the 2 x squared plus c to the 3 x cubed. And basically the c's represent the different coefficients for each term. And we can find the interval of convergence for this series using the ratio test.
So for our first problem, we're going to find the interval of convergence. You'll have to use the ratio test, and then so it's the limit as n goes to infinity of the absolute value of, and you substitute n plus 1 for n, so it'll be 2x plus 5 to the power of 2, and it'll be like n plus 1 over, and then n plus 2. And then you multiply it by the reciprocal because it's on the bottom. So n plus 1 over 2x plus 5 over 2n. Okay, so now we have the interval convergence, which you have to plug back in to the original equation, which was 2x plus 5 over 2n all over n plus 1. So you have to check the endpoint, so you plug in -3 into x. So we're going to use the limit comparison test to test this out. So it's the limit as n goes to infinity of 1 over n plus 1 times, and then I'll use n, so it'll cancel out and it'll just be 1, which is greater than 0, so it works. And then, so find the summation of n equals 0 to infinity of 1 over n, because you times it by n, and it'll be divergent by p series. So therefore, the original summation diverges by LCT, limit comparison test. So check the second endpoint, which is -2. We know that it also diverges by LCT. So therefore, the interval of convergence for this summation is -3 to -2.
One of the common power series that we talked about before, the summation from u to the n of n equals 0 to infinity equals 1 over 1 minus u, can be used to find the summation form of a function like f of x equals x squared over 1 minus x cubed. So the first thing we can do is we can try to evaluate this function so it's as similar as possible to this 1 over 1 minus u. So the first thing we can do is factor out an x squared to make it 1 over 1 minus x cubed. And as you can see, it looks very similar to this function. So we can leave the x squared out of the summation form and put x cubed to the n as our summation, since the x cubed here matches the u here. So from here we can simplify it by putting the x squared into the summation form. So we can turn this into n equals 0 to infinity of x to the 3n just by multiplying the 3 times n. And by bringing in the x squared, we can add 2 to the exponent of x to the 3n. So the final answer is this.
Hi, I'm Alex, and Serena already introduced this idea of power series, and this is actually one of the more common power series that we see. It's f of u equals 1 over 1 minus u, and that equals the summation as n starts at 0 to infinity of u to the n. So we're going to use this formula to prove that this is true. So we can do that by first taking the derivative of this, which equals 1 over ln plus u. So we're going to do this by finding the derivative of this, which is 1 over 1 plus u. And then we know that this equals 1 over 1 minus negative u. right? So you can see how this looks similar to this. So we can just use this formula, summation n equals 0 infinity, but instead of a positive u, we have a negative u here, so we use negative u to the n. And since we took the derivative over here, we're going to take the integral of this. So the integral of negative u to the n, that equals u to the n plus 1 over n plus 1, just inverse power rule here, and since we have this negative here, we're going to bring it up, we're going to bring this out as a negative 1 to the u, and that ends up being negative 1 to the n. Or negative 1 to the n. We bring it out as a negative 1 to the n because it's multiplication. You can just distribute that n. And this is all summation. Yeah, that's a summation sign. Deal with it. Okay.
For this problem, we'll have to find the coefficient for the 11th term. So first we have to write the Taylor series for this tan inverse of 2x. So here's the formula that we have to memorize. And so it will equal the summation from n equals 0 to infinity of negative 1 to the n of 2 to the 2n plus 1 x to 2n plus 1 all over 2n plus 1. And then I just split 2 and x, so it'll be nicer like that. And then for the 11th term, 2n plus 1 here has to equal 11. So when you solve for n will equal 5. Okay, so now to find the coefficient for the 11th term, you just plug in 5 for everything else. So it'll be negative 1 to the 5th of 2 to the 11th over 11. So it'll be just negative 2 to the 11th over 11.
The next question is asking to find the Taylor series for the following function at a equals 2. So based on what I said before, how the Taylor series is represented in this following format, we can use what we know about first derivatives, second derivatives, and so on to express this in the form of a Taylor series and then express it later in the summation form. So the first step you're going to take is find the first derivative, second derivative, and basically enough terms that will give us enough information to put it into summation form. So at n equals 0, we know that the function is going to remain as f of x, and f of x, as we know before, is 3x to the negative 4. And if we evaluate it at a equals 2, we know that this will equal 3 over 2 to the 4th. For n equals 1, we know that f prime of x equals negative 12x to the negative 5th, which equals negative 12 over 2 to the 5th at a equals 2. We will repeat this step for f double prime of x and f triple prime of x. So now using the coefficients I found using the derivatives, I can express this in terms of a long chain of multiple terms. So therefore, our f of x would equal 3 over 2 to the 4th times x minus 2 to the 0 over 0 factorial. So I'll just keep adding the coefficients in until I get a chain of a polynomial chain. Know that our terms are going to start from 0 to infinity, and as we can see, the x minus 2 for each term increases by the factor of n. So we can have x minus 2 to the n in our numerator, and for the denominator, like seen before, we have our factorials for each term. So we can add a factorial of the nth term to the denominator. And we can now, looking at the other coefficients, we have 2 to the 4th, 2 to the 5th, 2 to the 6th, and 2 to the 7th. So basically, the 2's are increasing with an exponent for each term. So since we start off with 4 here, and it's the 0th term, we're going to have n plus 4 as our exponent for the 2. Since for the 0th term is 4, and then increases by 1 for each term afterwards. And as we can see, it starts off positive for this term, negative, this is supposed to be positive, and negative. So we know we're going to have a negative 1 to the n in our numerator as well, since it oscillates from negative to positive. And to determine how we can express the other coefficient, 3, 12, 60, and 360, we're going to use what we know about factorials. So as we can see, the first term is 3, the next term, 12, is 3 times 4, the term afterwards is 3 times 4 times 5, and 360 is 3 times 4 times 5 times 6. So basically this looks like a factorial, except we don't have our 1 and 2. So we can express this in terms of, in our numerator, n plus 3 factorial, and since we don't have a 2, we can divide this term by 2. And we already have a 2 in the denominator, so we can remove the 2 from here, and we can add another 2 to the coefficient of 2 in the denominator to make it n plus 5, giving us our final answer of x minus 2 to the n, negative 1 to the n plus 3 factorial over n factorial times 2 to the n plus 5. So based on what we know about power series, we can use the formula as shown to find the error for that certain power series. So if a question asks you to find the error for a certain power series, they will give you a certain interval, let's say from C to D, and they will say about A equals a certain value. Let's call it B. So we want to maximize this error as much as possible. So based on the interval that we're given, we want to plug in the value into f of n plus 1 to maximize it, and the same for c minus a to the n plus 1 to maximize it. And a again is the value that is given to us. So using this formula, we can find out how close our approximation is to the actual summation of the power series.
Mistakes that often appear in our topic are minimizing when you needed to maximize in the Lagrange error. So remember, you have to maximize this here, and you have to maximize this. There's no minimizing in Lagrange error. Another mistake would be writing this 2n plus 1 instead of 2n plus 1. Remember that you don't just add 1 to the exponent, you're adding 1 to n. So you need to put parentheses around it, because when simplified, this turns into x to the 2n plus 2, if you distribute that 2. And our third and final common mistake is forgetting a in the Taylor series. That would be this a here. Oftentimes people will just write it without the a and just do like x to the n, but they won't have they'll have a non-zero a. So they got the problem wrong. And those are common mistakes.
Here are some helpful hints that will guide you in solving power series. So the first one is that you can never express a chain of polynomials in summation form. Like let's say you have the function x cubed plus 4x squared, and so on. It's impossible to put this into summation form. It's because the derivatives eventually reach 0, so there's no pattern in writing in the summation form. The next one is sometimes the summation form will start with the term n equals 0, and once you plug it in, the first term would be 0. So in order to avoid that, we can change the bounds to make it one term later, so you're guaranteed to get a non-zero term. Or you can add n plus 1 to the exponent, that will give you a non-zero term. And then the last tip is to utilize ln functions in order to solve power series. So we know that ln of 1 plus x can be expressed in a power series. And in order to get it as similar to that as possible, we can take a function like this and factor out a u. And based on what we know about ln, we can take out the u out of the ln of u plus u times 1 plus x and put it into a sum of two ln functions.